In the previous video, we looked at a couple of different atoms. Say, for example, we take an atom of lithium, and if we study its electron configuration, well, we know that lithium will have 3 electrons. So here they are drawn as X's, where its arrangement is 2 in the first energy level, and then it's got 1 in the second energy level. And when you pair that up with another atom, particularly an atom from the right-hand side of the periodic table, a non-metal atom, say something like fluorine. Fluorine has 2 electrons in its first shell of electrons, drawn as dots here. And then in the second shell of electrons, it's got 7. 1, 2, 3, 4, 5, 6, 7. We learned that atoms are very stable when they've got a full outer shell of electrons. Now for the second shell, this one here, a full outer shell is 8 electrons. And for the first one, a full outer shell is 2 electrons. So we've learned all that before we learned how to draw atoms. So what's going to happen in this case is for both of these atoms to be as stable as possible, fluorine, the non-metal atom, is going to remove an electron from the lithium. So this outer shell of electron is going to go from lithium and it's going to be taken by the fluorine. And what this does is it creates this situation where we've now got 8 electrons in the second shell of fluorine, and it's now it's got a stable octet or a stable electronic configuration. And now this electron has been eliminated from the lithium, and so has that second energy level now, essentially. So now this lithium has a full outer shell of electrons, because it's outer shell of electrons. And this is why this happens. This is why the transfer happens, because both atoms are left more stable afterwards. We can predict, just before we do, we know that what that does is it creates this situation where we've now got a lithium plus ion, and we've got a fluorine minus ion, because the fluorine has taken an extra electron, so it now has 1 extra negative charge, and the lithium has lost an electron, which means it's got 1 extra positive charge. And these two things then will stick together, and this is what we call an ionic bond. And this is now an ion. This is why these make an ionic bond. Now, when we're forming ions, we know we can tell what type of ion is going to be formed by looking at the periodic table. Here are the group numbers: 1, 2, 3, 4, 5, 6. Oh, that's a bit close. I'm going to just fix that. 6, 7, and 8. All right. Because everything in group 1 has 1 electron in the outer shell, like lithium, they will always form a +1 ion. The ones in group 2, those have 2 electrons in the outer shell, and these will lose those 2 electrons to become a +2 ion. Guess what? The third energy level, they have 3 in the outer shell, and they become a +3 ion. Now, group 4 do not form any ions. They have 4 in their outer shell, and they don't do this type of bonding. We're going to see different type of bonding that they do later. Group 5, well, these have 5 electrons in their outer shell. They could lose all 5, but it's usually easier to gain 3 to make 8. So these will become a -3 ion. Group 6 will become a -2 ion because they've got 6 in the outer shell, gain 2 more. They can become, they have a full stable octet, so they become a -2 ion. And group 7, like this one here, like fluorine, 7 electrons in their outer shell, so they will become a -1 ion. Group 8, they don't do any bonding. They've already got 8 electrons in their outer shell, or they've got a stable octet. They don't want to do any bonding, so they don't form any ions. So this here is what we call the valency table. This tells us valency. This tells us what type of ion or how many bonds they're essentially going to form. Atoms of these different groups. Another thing to point out is that this here is a metal atom, and everything on this side of the table down here, groups 1, 2, and 3, these are usually the metals, and they always become positive ions, as you see. And here, this is a non-metal atom. It's on the right-hand side of the periodic table. We've seen that before, and it's usually over here, groups 5, 6, 7, or 8 on the non-metals. So when we pair a metal and a non-metal together, we usually get an ionic bond. That's a general. So when we've got a metal atom with a non-metal atom, and they're coming together in the same area, generally the non-metal atom is much more attracted to the electrons, and it's going to transfer the electrons, take them away from the metal atom, and you're left with these 2 oppositely charged ions that are held together by an ionic bond. But what happens when we don't have a metal and a non-metal? What happens when we've got something like this? Say, here is an atom of hydrogen. Hydrogen has 1 electron in the outer shell. Here's a second atom of hydrogen. It's got 1 electron in the outer shell. These are 2 non-metal atoms, and they're both the same atom, which means that neither of them has any particular extra attraction for the other one's electron. They both have the exact same attraction. They're both non-metals, they're both the same atom, so they both have the exact same, what we call affinity for the 2 electrons. So in this case, neither one of them is going to have the ability to transfer or remove the electron from the other one. So in this case, what happens is that the two electrons actually end up being kind of shared in the middle between the two hydrogen atoms. We often show this as a bond, like this line here, we call this a bond. But what this actual line represents is that shared pair of electrons. There they are. They've been shared in the middle of the two atoms. Now, if you consider for a second each atom, we could say that this atom here now has a share of 2 electrons. It doesn't have the 2 of them to itself, but has a share of the 2 of them. And this atom here also has a share of 2 electrons. So what we actually call this here, these 2 electrons, we call this a shared pair of electrons. A shared pair of electrons. That's what the bond represents. Each of these is an electron, and the pair of them are shared in between. And every time you see a bond drawn with a line like this in chemistry, we're talking about a shared pair of electrons. Okay, so this is what we call a because co means cooperating, valent. Valent to do with valency, because they're to do with the valent shell electrons, the ones in the outer shell. These are the ones that can be shared. Covalent, this is a covalent bond. So it's going to hold these 2 atoms together because both of these, I'm just going to get rid of these 2 circles for a second. Essentially, both of these atoms have positive nuclei, and these positive nuclei are going to be attracted to the 2 negative electrons. And that's the same in both cases. So these arrows are showing the attraction, and here's the green arrow. Obviously, negatives attract positives. So this here is showing that both nuclei are attracting the negative electrons, but they're both pulling them with the same strength. So they end up being stuck in the middle. And that's how they end up being stuck together, because the both atoms are being attracted to the 2 electrons in the middle. So this is a covalent bond. Now, both of these atoms here are non-metal atoms. So when you've got a non-metal, like hydrogen, like another hydrogen, or you could replace that with oxygen, you could replace it with fluorine, with chlorine, whatever you want, you're going to get a covalent bond. So that's the second general rule. So at this point, what we're going to do is we're going to just get you guys to take down the definitions of ionic and covalent, or the general rules. You see it here in red. I'll start beside just here, this general rule. So pause the video and take down that general rule now. Okay, again, big picture in case I haven't made it clear enough. Why are the atoms doing this? The atoms are doing this so that they can become more stable in their electronic configuration. They want to gain a full outer shell of electrons. Both of these atoms here now essentially have a shared pair of they have a pair of electrons. Hydrogen only has 1 electron, so to fill its first shell, it needs to get 2. So again, I'll show you another way that sometimes you'll see this drawn. You'll see here's the first shell of electrons. Here's the X belonging to the first atom, and the second atom is right alongside it. And here's its electron. Maybe I'll just do it in a different color so it's more clear. So I'm going to draw the electrons in black instead of in blue, because I don't think they're coming up very clear right now. Sorry, my pen is struggling to change color here. Okay. Yeah, that's not playing ball with me, so I'll just have to go with it. Okay, so you see here, hopefully you can see the 2 electrons in the center here, the dot and the X. And those are the electrons that belong to the 2 hydrogen atoms, been shared in the middle, and both of them now have a share of those 2 electrons in their outer shell. We need to be able to learn how to draw a diagram for covalent diagrams, just like we learned for ionic diagrams. We call them, because we're going to use dots and crosses, we call them dot and cross diagram. But just like ionic bonds, we learned how to draw an ionic dot and cross. In this one, we're going to learn how to draw a covalent dot and cross diagram. So how to draw a covalent and cross diagram. Now, you may also sometimes see this. Lewis structures are just the diagrams that show the electrons as dots and X's. So sometimes you'll see it being called that. Now, this is really annoying that my pen won't change color, because I'm stuck with just one color then. But anyway. Okay, so we're going to look at an example of an atom that I'm just going to pause the video, see can I get my pen working. Really sorry about this, guys. We're back. I think we're fixed now, so we're good to go. Let's take an example of, say we have this example where we have chlorine. So this is a chlorine atom. The first thing we should do is look up the electronic, or look up how many electrons the atom has, and figure out how many electrons has it got in its outer shell. So we're not going to do the full drawing of the atom with all the shells. We're just going to draw the valence electrons. We did this as well for the ionic dot and cross diagram, so you should be familiar with this idea. And if you figure out chlorine's in group 7, it's got 7 valence electrons. So here we're going to draw them as X's. So this chlorine has 7 valence electrons. Now, obviously, that does not satisfy the octet rule. Again, it's in group 7. It's got 7 valence electrons. Just to show that they're different, they belong on a different atom. I'm drawing them as dots here. And what we've got here is 2 non-metal atoms. So definitely not going to be ionic because both of them would form a -1 ion and they won't attract each other. So it's not going to be ionic bonding. So what happens here? Well, obviously, we can see that neither atom satisfies the octet rule. So neither atom be on the lookout to try and become more. And what happens is that they will interact with each other and they will share a pair of electrons. So the first thing we'll do is, well, they're in group 7, so both of them just need one more. So if they share a pair, one each, then they would have a full outer shell of electrons. Watch how this works. Let's draw the 2 chlorines and set them up so that they're going to share a pair. So this one leftover electron here, we're going to put in a nice position so we can share it with this one electron here. Now remember, this line has to represent a shared pair. It can't be just one electron, it has to be a pair. So this here is the 2 chlorine atoms and they're now sharing a pair. Now draw the rest of the electrons that each atom has of its own. So chlorine has 6 other X's of its own, and this chlorine has 6 other dots of its own, like this. Just do a quick count on the electrons now. Okay, we're going to do how many electrons does this atom have first, and then we'll do the other one. Okay, so it's got 2 here. It's got 2 here of this shared pair, which is 2 more, obviously. So that gives this chlorine on the right a total share of 8 electrons. So now this atom is satisfying the octet rule. Because the atom is the same, it's another chlorine, it's the exact same. It's got 2 of its own here, 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 and then it's got the shared pair that it's got to share of. So again, it's got 8. So we've gone from a situation where neither atom satisfies the octet rule to now both atoms satisfy the octet rule. And this is why they will do it, because it makes them more stable. It makes them satisfy the octet rule. So again, we've got 2 nonmetals. The general rule is any 2 nonmetals, that's what you got to check first. Am I dealing with 2 nonmetals or am I dealing with a metal with a nonmetal? That's the general rule that's going to help you figure out, is it ionic or is it covalent? What we're going to do is you're going to have a go at this little one for me now. You do, actually, I'm just going to do it underneath. I'm running out of space here a little bit, but you're going to do this one for me. Show, you following the method that I just did, show the ionic or the covalent bonding in F2. So begin by drawing the Lewis structures of the 2 Fs, so that's with dots and crosses, and then draw the 2 Fs sharing a pair of electrons. So pause the video and do that now. I'm just going to pause myself so I'll go get a charger. Okay, so what you should have done is you should have drawn, first of all, the first F. So here it is. And you should have drawn the valence electron diagram, so the Lewis structures. Now remember, you only draw the outer shell electrons when you're doing this. So this is just a little shortcut. Instead of drawing all the shells of electrons, because sometimes it could be 3, 4 shells of electrons. And remember, it's only the outside ones that do any bonding that are ever involved in moving or sharing. So you only need to draw the outer shell ones. So fluorine, again, first of all, what group is in? It's in group 7. So that means, again, it's got 7 valence electrons like this. There they are. And the second fluorine, because this is F2, which means we'll have 2 fluorines, 4, 5, 6, 7. Okay, so 2 Fs. Now, if you didn't know how to start that, fair enough. I want you to pause the video and take this down now. Okay, and if you haven't already, what I want you to do is now show how they share a pair of electrons so that they'll both achieve a full octet, or they both satisfy the octet rule. So pause the video and do that now. Okay, so in this case, they're both in group 7. They need 1 more electron each, which means if they share 1 pair like this, so set it up so that they share 1 pair, and they each obviously keep all of them. they've now satisfied the octet rule. So this is what F2 looks like. So this is what happens in a molecule of F2. They have a shared pair. Right, the last thing I want you to do here now is just label the shared pair of electrons here. Do that now. Okay, so what you should have done is labeled these two as the shared pair. Now, just as an aside, what are these other ones called? Notice that we've drawn them all in pairs. Well, these are called lone pairs, and they're a lone pair belonging to each fluorine. That's going to help us later on. All right, let's try another one. Let's try HCl. So just begin by finding out how many valence electrons each one has and draw them, and then show how do they combine together using a covalent bond. Pause the video, do that now. All right, so what you should be looking at here is hydrogen has 1 electron. So there it is, 1 electron just. Here is the chlorine. We learned already chlorine's in group 7, 7 valence electrons, and here they are. Again, they're 2 non-metals. Okay, so there was 2 options here. They could have done ionic bonding or they could have done covalent bonding. So the chlorine may have taken the electron from the hydrogen to form ions. And that is not what happens here. These are 2 non-metal atoms. That one's a little bit hard to tell, and later on we're going to see a more accurate way of measuring this, not just whether they're metals or non-metals. But for now, the general rule is 2 non-metals, it's not ionic, it's covalent. So now we need to, if you haven't done that, if you did ionic, you need to stop and you need to show covalent bonding. So pause the video and finish it off if you haven't got that right. Okay, so here we go. This is what we have. Set the 2 atoms up, and again, they're going to share a pair of electrons. Now, they can only really share 1 pair because hydrogen's only got 1 electron to share. So there is the shared pair. Notice that this hydrogen now has a share of both of these. So it's got a full octet now. That full first shell is full. And the chlorine has the shared pair, but it's also got 3 lone pairs shown in blue here. These are the 3 lone pairs. So it's got 3 lone pairs, 2 electrons, 2 electrons, 2 electrons, and then a shared pair is 8. So again, both atoms satisfy the octet rule. Right, I'm going to show you what happens when we have something a little bit more complicated than this. Let's take example O2. Okay, so in oxygen, again, we're going to have 2 atoms, which are non-metals, so it's going to be covalent bonding. I'm going to begin by drawing the 2 atoms. And I'm going to get you guys to pause the video, and in a second when I ask you to, and we're going to draw the valence electrons on the 2 oxygens. Just the valence electrons, use dots on one and crosses on the other. Pause the video and do that now. All right, so what we should have here is on this oxygen, I'm going to use X's, you might use dots, that's fine. 6 valence electrons. Hopefully you got that right. And this oxygen also has 6 valence electrons. They're in group 6. So the shortcut that we taught you before, whatever group they're in, that's the number of valence electrons that they have. So 6 and 6. Now, when we put these 2 things together, I told you they're 2 non-metals, they're going to do a covalent bond. So how is this going to work? Well, let's set them up so that they share a pair of electrons like this. Here's the 2 oxygens, and let's see them share a pair of electrons. So there it is. That's a little bit far apart, and it looks a bit silly. So I'm going to put them a bit closer together. Here it is. So here is them sharing a pair of electrons. Okay. Now, remember what group they're in. They're both in group 6. So really they need 2 more each. Okay. It's different from the chlorine and the fluorines above because they only needed 1 more each. This one needs 2 more each. So you're going to see in a second that this doesn't quite work. And sorry, I've got my dot on my X the wrong way. So I better fix that. The X is on this side and the dot's on that side. Oxygen's other 5 like this. Now, if you count all the electrons each atom has, you're going to see that this isn't enough. Neither of them have achieved the full octet yet. Neither of them are stable. You've got 1, 2, 3, 4, 5 X's, and then 6 and 7, a share of them too. That's only 7 electrons, and it's not enough. And the other atom is going to be the same. So what happens here is because each one needed another 2, they're going to share a second pair, like this. Now, if you count them up, you should see that each oxygen has achieved a full octet by sharing 2 pairs of electrons. These are 2 shared pairs. And this is what we call in chemistry a double bond. This is a double covalent bond. We see this type of thing all the time. This is not rare at all. So two group 6 atoms like this will form a covalent, double covalent bond. I'll just count them all. Here's a shared pair, a lone pair and a lone pair, that's 4. And then two shared pairs, there's 4 more. So this oxygen on the left has 8 electrons. The other oxygen is the exact same, has a share of 8 electrons as well. So again, this is why atoms do this, to become more stable. You try this one, see can you figure it out. 2 nitrogen atoms. So using the method that I used above, it's a little bit more difficult, but you should be able to do it. Pause the video and do this now, have a go at it. Okay, so the first thing you want to do is with the 2 nitrogens is you want to draw their valence electrons. Nitrogen is in group 5, which means it's got 5 valence electrons. So 1, 2, 3, 4, axes again, I need to go dots. Sorry, nitrogen with dots, 1, 2, 3, 4, 5. Now remember, they need 3 more each. These needed 2 more each. They wanted 2 more each, and these want 3 more each. So if they want 3 more each, then we're going to share 3 pairs of electrons. Hopefully that's what you did. When you add these 2 things together, you get the nitrogen, and we've got to set them up to share 3 pairs of electrons like this. Then don't forget about the rest of them that belong to them themselves. If we're sharing, we're already using 1, 2, 3 of these in a shared pair, then there's 1 pair left. Okay, so we need to make sure we don't forget about that single lone pair that they had left. So each atom should have 5 of its own electrons, so 5 x's, 5 dots, and are sharing 3 pairs in the middle. This is what we call a triple bond. So in nitrogen, we find a triple bond. All right. Let's take an example where it's not just as straightforward as that. What if we are forming a bond between hydrogens and oxygens, H's and O's? Again, both non-metal atoms, so it's going to be covalent. What we're going to do is we're going to go ahead and we're going to draw the electron configuration, just the valence electrons again of hydrogen and oxygen. Pause the video and do that now. Okay, so you're going to have a hydrogen and an oxygen like this. Oxygen has only 1 valence electron. So what you will probably be tempted to do is you'll probably be tempted to go, okay, here we have our oxygen, and here it's going to share a pair of electrons, and then the hydrogen's good now. The hydrogen has a shared pair, which is 2, and that fills up the valence electron of the hydrogen. Now the oxygen has 5 other electrons of its own, like this, 1, 2, 3, 4, 5. And that gives the oxygen a total share of 1, 2, 3, 4, 5, 6, 7 electrons, which is not good enough. Now, it can't share another electron with the hydrogen because the hydrogen doesn't have another electron. It only had 1. So it can't share it with, and it can't share a second pair of electrons with that hydrogen. Well, what it could do is share a pair of electrons with a second hydrogen. And that's always possible because when we're talking about mixing chemicals together, we've got large numbers of atoms. So in this case, what we're going to have is a second hydrogen sharing a pair of electrons with the oxygen like that. So now we've got an oxygen with 2 hydrogens, and we're sharing a single pair with each hydrogen. This gives us the substance H2O because there's 2 hydrogens, 1 oxygen, and that would be the structure of it. Now, technically, that's not drawn very well. This would be better if we put the oxygen here and we make sure this is typically how you'll see it drawn. Just a little bit neater, and then the 2 lone pairs up here on the oxygen. Technically, that's a little bit better, but it's the exact same as what's above. It's just neater and tidier. All right, guys. So what I'm going to get you guys to do is have a little practice at a few more. You guys see, can you figure out this one here? CO2. That's the final substance. So see, can you draw the covalent dot and cross structure for how this forms, CO2? Try this one now, CH4, and then try this one, NH3. So pause the video and see, can you draw the final structures of these substances? Pause the video, do that now. Okay, so carbon is in group 4, which means it's got 1, 2, 3, 4 valence electrons like that. Oxygen is in group 6, which means it's got 1, 2, 3, 2 of them. So here's the second one, 1, 2, 3, 4, 5, 6, like that. So when these join together, what's going to happen here? Well, carbon needs a share of 8 electrons. It needs 4 more. So it's actually going to have to share 4 pairs to get a full octet. Oxygen each need 2 more. So this is how this is going to work. We're going to have our carbon, and it kind of goes in the middle, and 2 of the electrons are going to go to share with 1 oxygen on the right, and 2 electrons are going to go to share with 1 oxygen on the left. Here are the 2 oxygens. There's the first one. There's the 2 lone pairs, and just check the electrons again. This oxygen on the right here should have a share of 8 electrons altogether. And one on the left is going to be the exact same. 6 valence electrons of its own and a share of 2 more. Yeah, and now just check the carbon in the center. It's got 4 valence electrons of its own, and it's got 4 that are shared. So it's got 4 shared pairs of a total of 8. So that's what that one's going to look like. Tricky enough to do that one. What about CH4? Well, we know carbon again has 4 valence electrons like that, and hydrogen has 1 valence electron like that. So when we add these 2 things together, what we're going to get is our carbon, and usually the one that we have in the middle, we call these the central atoms. So we put it in the middle here, and then we work the other ones around it. So hopefully you can see by now that it's going to share a pair of electrons with the first hydrogen, then it's going to share a pair with the second hydrogen, then it's going to share a pair with the fourth hydrogen. Remember, each hydrogen wants a share of 2, and they have it, just check that. And the carbon wants a share of 8, and it's got 4 shared pairs around it, so it's got a share of 8. Last one, a little bit tricky. I think this is the hardest one, so do make sure you've had a go at it. Pause the video and make sure you have a good go at this now. The first thing I want to do is draw nitrogen. Nitrogen has 5 valence electrons like that. 1, 2, 3, 4, 5. And it's combining with 3 hydrogens. Here they are, the 3 hydrogen atoms. All right, so what we're going to do here is we are going to put the nitrogen in the middle and hydrogens around it. Okay, so again, share a pair with each hydrogen. Now, there is a reason why I'm going to draw this with this shape. You might not have drawn it exactly like this. This is the... So there's our 3 hydrogens being shared. We've got 6 valence electrons in the shared pairs for nitrogen, and it also had 2 more of its own. We've only drawn 3 of the valence electrons here of nitrogen, and we started at the beginning with 5, so it also has a lone pair. So just check nitrogen now for 8 valence electrons around it, 2 here, and then 3 shared pairs. So that's 3 pairs is 6, and the lone pair is 2. That's 8 electrons on the nitrogen. All right, guys, so that is covalent dot and cross diagrams. We do need to be able to draw them. We do need, especially we need to be able to draw the final structures like these ones here. But to be able to figure that out, you do need to be able to kind of draw the valence electrons and figure out how many of each are going to combine to make your final molecule. All right, guys, that's covalent bonding. We will kind of build on this idea, make it slightly more complicated in the next lesson, but that's the basics of it for today. We'll see you in the next lesson.